Hi, this is Corey Bauer, Application Engineer for GoEngineer. In today's webinar, we are going to look at pipe flow analysis. In the next 30 minutes, we're going to look at 3 different examples. The first example is purging some existing gas out of a piping system. The second example is mixing fluids, so multiple inlets with different fluids coming into each one of them. And the last one is looking at stress and deformation based on the pressures from the flow.
So here is our sample full piping system. So in this particular case, this is the one that's going to have the residual gas in the piping system that we want to purge out. So in this case, down here in the lower left is going to be where the fresh nitrogen is coming in, and then on the T up top is 2 outlets where that residual gas will get purged out, and then pure nitrogen will start to flow. Okay? So a couple of things besides just the mixing of the fluid, we need to kind of watch the whole process, so that's going to make it a time-dependent study on top of being, mixed fluids. So first thing we're going to do is run through the wizard and see how we get the basics set up. Okay. So we run through the wizard. We give the project a name. We decide what configuration we want that tied with. Okay. Of course, we pick our units that we want to use. Okay. And here's the first of what we need to set up specifically for the 2 things, the mixing and the time dependent. So by default, every project that you create is going to be steady state. But for this one, we do need it to be time dependent. So we're going to turn that option on. We give it a total physical time that we want to run the project over, and then we also give it the time steps that we want results generated. Okay. So in this case, it would be a 1-second analysis taking or recording results every 10th of a second. Okay. So that's how you set up your transient analysis. Okay. The next part is where we set up our multiple fluids that we want to use. Okay. So we're going to use ethane. We're going to use methane, and we're going to use nitrogen. Okay. Now, whether we want them all to be the default or if we want just one of them to be default, it ultimately depends on what we're going to analyze, which would be the best case. In this case, because we're going to be using all 3 fluids all the time, it's easiest just to go ahead and let them all be the default. Okay. We can decide how we want to treat the walls in our system, so perfectly insulated, or we could have some kind of heat flux defined leaving the system, or a heat transfer rate leaving the system, or some constant wall temperature. Okay. We're just going to have insulated. And we could add a roughness to get even more accurate results. Okay. Now this next step is something that we typically do not make any settings for an internal flow like this one, but here we do have to make a setting, and that is in the concentrations area. Okay. So because we picked those 3 fluids all being the default, it automatically splits it into the initial volume being made up of 1/3 of each of those gases. Okay. Well, in our case, that's not quite the way the system is. So at the beginning, we don't have any nitrogen present because that's used to purge it out. And then we're going to have, say, 50% ethane and 50% methane. Okay, so on the very first time step, the mixture in the pipe is going to be half ethane and half methane. Okay. To introduce the nitrogen into the flow, we do that during the inlet condition when we define that. Okay, so again, two key things when we set this up was total time and then the output step and what we want our initial concentrations to be. Okay. So I'm going to go ahead and go to the already set up study. Okay. Now in this one we did have not 50-50, so it ended up being 25% ethane, 75% methane, and still 0 for the nitrogen. Okay. Now, when we define our inlet, okay, so in this case we've got a volume flow rate that's entering in the piping system. Okay. And again, for an inlet, it could be a mass flow, a volume flow, or a velocity. And then we've also got a section now, because we had multiple fluids defined, or substance concentration. Now, you're only going to see that added to the menu when you pick multiple fluids. Okay? And the same thing happens here. We define the percentage of each of those, in this case gases, are entering the system. Okay? So 0% ethane and methane, 100% nitrogen flowing in. Okay? So what that means is for this setup, the methane and ethane are only there in the full volume initially, and then they get purged out with the nitrogen. So no new ethane and methane are getting introduced. For our outlet, it's just simply being dumped out to atmospheric pressure. Okay, so through that face and that face. Now I didn't set up any goals when I initially did this, but typically when I'm doing a mixing problem like this, I will set up a goal for the mass fraction of the fluids, okay? Because that's what we look at as far as mixing. And we'll get into what that means here in just a second when we go into the results. Okay, so the question is for the outlet, is there any concentration settings? So in the menu, there is, okay? But here's where it gets a little bit tricky, or you just have to remember. When you do substance concentrations, if it's an inlet, what you enter in is forced. When it's an outlet, that concentration that you enter in is just the starting point for the calculation. So what that means is you are not controlling the concentration out. The software is calculating that for you. That's typically what you want to know on a mixing type of project is what is the concentration that leaves. Question is, if ethane had been water and gravity is turned on, would the simulation have started with the bottom of the pipe with the methane on top? Well, the first thing is we cannot mix gases and liquids. So if we were introducing water into it, the other fluids would have to be liquids as well. Now, as far as saying they were all liquids with gravity turned on, initially they would still be completely mixed, completely homogeneous. So no, the heavier liquid wouldn't be down at the bottom initially, but it would, as you ran through the analysis, it would tend to settle out. Okay. So the first thing before we jump into specific results is, in general, when you are doing a time-dependent study, which is what we're doing now, we can only look at one time step at a time. Okay, so that's why you may notice that next to the result folder, in parentheses, we also have the time step that we're currently looking at. Okay, so this is the results for half a second into the analysis. Okay. If we wanted to look at a different time step, you just right-click on the results and load a time moment, and that now gives us a drop-down for every output result for that entire project. Okay, so we could look at our slices. Let's go ahead and look at one early on. I'm not going to go with the first one. I'm going to go a little bit in. That way the nitrogen has started to flow. And we've got our cut plot of nitrogen. Okay. So the result that we use for tracking the way the fluids are mixing, it's one of two. It's either the mass fraction of a particular fluid or it's the volume fraction. Okay. So in this case, we're looking at the mass fraction of nitrogen, and we are 0.01 seconds into the analysis. So it's telling us that the red area is 100% nitrogen, and then as it goes down to dark blue, it's still 0% nitrogen. Okay. If we look at, say, methane, we can see, just as we defined, it is 75% through most of the pipe. Where the nitrogen is starting to push it out, you can see it's got a lower concentration. If we looked at the ethane, okay, we're at 25%, and again, we see where the nitrogen is starting to push it out, it's at 0%. Okay. So that's how we track the way the gases are mixing. Okay. Now there is one way that we can look at all the time steps kind of stitched together, and that's if we animate one of the plots. Okay. So the way we do that is we pick whichever one we want, which nitrogen is kind of the main fluid we want to look at first. So we will animate that fluid, or that cut plot for the fluid. Okay. There is a wizard to set up the animation. So the first thing we want to do is, how long do we want the animation? That this is completely independent of the length of the project. This is just simply how long we want the video to be. So it's either going to be the results slowed down or sped up, depending on what the time of the analysis was. We want to delete all existing tracks. So as it loads in the new result, it'll get rid of the old one. Okay, we could have it rotate the model, but in this case, we don't want that. Okay. And the way we get it to load one after another, the time steps, is to use the option for scenario. Okay. So our analysis was half a second. So we can look at that entire analysis, or we could look at, say, the first half, whatever we want to see. Okay. So if we look at the timeline, because the result files were so close together, it looks like it's just a big green line, but what it really is a bunch of green diamonds stacked together. Okay. Each diamond is where it adds in the next time step. Okay. So the green line, the green diamonds are loading the results, but we still have to tell the software what plot we want animated. So we just line up with the cut plot for nitrogen. At time 0, we want to insert a control point, and we'll drag it out to the end of the animation. Okay. So there you can see as nitrogen turns on, purges out. Okay. In this case, this little branch of the T that dead ends, okay, that has trapped some of the original gas that we wanted to purge out, okay, simply because it had no place to go. Okay. So that is the first example of multiple fluids time dependent. Okay, but again, that was some residual gas, but only one gas new flowing in. Okay, this next example that we're going to look at is multiple inlets, each one having one of the gases flowing in. Okay, so the wizard setup was identical to what we already saw. I'm just going to show you the basic stuff that we had set up. Okay, so it is time dependent. Now in this case, it's basically an even mix of ethane and methane. I did 30, 30, and 40%. So that's the entire volume is going to be homogeneous mixture, or nearly homogeneous, 30, 30, and 40% of ethane, methane, and nitrogen. Okay. So on our boundary conditions, this lower one, I'm still having the nitrogen enter there. I'm using a mass flow rate, and I just picked an arbitrary 1 pound per second. In the substance concentration area, so it's 0% ethane, 0% methane, 100% nitrogen. Okay. Now, just to make it a little bit more interesting, I have it set up to where it's a different flow rate for each type of gas. So this is 1/10 of a pound per second of methane. And it's 1/2 a pound per second of ethane on this side over here. Okay. The outlet for the whole system is this top port, which we weren't using in the previous analysis. Okay, that's just emptying to atmospheric pressure. Okay. Now, in this one, I did set up goals for the mass fraction of each of those materials, each of those gases. Okay. Again, because it is time dependent, we can only load one time step at a time. If we wanted to look at another one, it's just load a time moment. Okay. I have my animations already created, so I don't have to run through the wizard again. I can just play them. Okay. So the first one we're going to look at is the mass fraction of nitrogen. Okay. So we can see, of course, in the inlet pipe here, it's going to be 100% nitrogen, and all the way up, it's going to be 100% nitrogen because we don't have any gas to mix with. But as it gets to the end, which I'll pause it. Okay. So here we can see there's just a small stream running through the middle that's 100% nitrogen, and as we go to the outside, it is mixing with the other two gases. Okay. And then to the left and to the right branch, it's 0% because that's where the other gases are coming in. Okay. If we want to look at the same thing for methane, it's going to be a much different looking plot. Okay. So you can see the methane really is staying to the left side as it flows out. Okay. Because its flow rate was much, much lower than the nitrogen. So the nitrogen is taking up most of the outlet. Okay. And then on the other side, the Now, again, I'll pause it when it gets partway there. Okay. Because its flow rate was, so 1 pound per second on the nitrogen, 1/10 of a pound on the methane, and 1/2 a pound on the ethane. You can see it has quite a bit more flow through the outlet. Okay. So that's a different example of fluids mixing. Okay. Now, the last thing we want to look at is if we want to take these pressures and input them as a load in a stress analysis. Okay. So the first thing you have to do is go into the flow simulation menu, go into tools, and we need to export these results out. Okay. If you forget that step, none of the pressure loading is going to be brought in to the analysis. Okay. So if we look at our static study, we've got it fixed up here at the top, and then we've got alloy steel for everything. And the key is when you right-click on external loads, we want to bring in the flow effects. Okay. And then the top part is thermal, which we didn't use, but certainly we could have. The bottom part is our pressure. So we want to include the pressure from flow simulation, and then we just have to tell it what result file to go get and bring in. Okay. And it creates the pressure and the shear stress loading from that. Okay. And then what we'll see is, this is an exaggerated scale, of course, okay, but because we've got this one corner, lower right-hand corner is blocked, you know, the pressure is really pushing on that. So that's what's causing us to deform like this. Okay, we could look at displacement. It's going to show us the same thing. Okay, so that's how we do a combination of pressure loading from flow and a stress analysis. Okay. So does anybody have any questions on what we've covered today? So 2 different ways of mixing fluids and then how to import those results to stress. Okay. Well, it doesn't look like we have any questions, so thank you everybody for attending this webinar on flow today. Thanks.